Why hello, today we're going to go on to section 17.8, which deals with Stokes' theorem. Now what is Stokes' theorem? Let's read what it says. Let S be an oriented, piecewise, smooth surface that is bounded by a simple, closed, piecewise, smooth boundary curve C with positive orientation. Let F be a vector field whose components have continuous partial derivatives on an open region in R3 that contains S. Then the integral along the curve, and it really would be nice almost to have a little here because it's an integral over a simple closed curve. You know, it's a closed curve that you're integrating, of f dot dr is equal to the integral over the surface of the curl of f dotted with the vector ds. Now exactly what's going on here, let me just show you. What we're saying here is if you have, maybe you've got some surface S that looks like this. Okay, now first of all, this is the surface. The surface is up here, and it's two-dimensional. Okay, there's your, really three-dimensional. Okay, there's your surface. All right, and then I have this curve C, that's the edge of the surface. All right, and I'm going to call that curve C. What Stokes' theorem says is if I integrate along the curve of f dot dr, that is equal to the integral over the surface of del cross f dot ds, is what it's saying. Now the only thing is that you have to be careful about is it says that the curve has to have positive orientation. Now what are we talking about positive orientation? Well, remember, when you do this surface integral, what we did last time, ds was equal to a unit normal times ds, where ds is your little surface area, but n was a little unit normal that was perpendicular to the surface. On this surface, if you look, you could have, if I put this little point right here, what would give me a normal to the surface? Well, I could have my normal going upward, or I could also have one just in the opposite direction, the other way. So we'll have to decide which way is your unit normal going to be going, okay? Now after you've decided which way your unit normal is going to be going, like maybe I want my unit normal to go upward that way, all right? Then positive orientation is the following. Think of a little guy walking along the curve. When he walks along the curve, this is Mrs. Strocko's way of doing it. When he walks around the curve, think of him having a cap on his head that's the unit normal. There's the unit normal on his head, all right? Now if the unit normal's on his head, all right, as he's walking along the surface, along the curve, he has to have his left arm pointing inward to the surface. So as you can see in this way, which way might be my positive orientation for the surface that I just drew? You'd have to go that way, right? For my little guy to be walking, for his left arm to be pointing into the surface. And he would have to be going around that way, all the way around, and back this way, so that the whole time his left arm will be pointing into the surface. You could say if I'm looking downward, it's going to be going counterclockwise, but I much prefer thinking of a little guy walking along. He has a little unit normal cap on his head, and he has to have his arm pointing inward to the surface. And so you have to have your orientation for the curve to be this way to equal this, because as we said, ds is n ds. So we have to figure out which way, which unit normal am I going, because every surface has two unit normals. So notice what this does. Now, why does anybody care about Stokes' theorem? What do we use it for? It's saying I can evaluate this integral by using this integral. Now, which way am I going to do it? Well, with you guys, if you have a take-home test or you have an in-class test and it says, use Stokes' theorem to figure out f dot dr, if you're going to use Stokes' theorem, you're going to say, oh, f dot dr equals the curl of f dotted with ds. So you're going to, instead of evaluating this integral, you're going to evaluate this integral, because Stokes' theorem says if you do this one or this one, you're going to get the same answer. Now notice what I think is pretty cool. What C is the edge of the surface, right? And it's saying the integral over the surface of the curl of f dotted with ds is equal to the line integral along the edge. Well, there's more than one surface that has this curve as its edge, I could take a surface that doesn't go out so far. You with me? You could just go up to about this high. And we can call him S1. And we could have another one that's much higher, and we could call that S2. And as you can see, for all of them, they're all going to equal this integral, this line integral along the curve of f dot dr, which tells you that the curl of f dotted with ds of surfaces that have the same edge are going to have the same answer. And so sometimes if you have one like this to do and it's really hard, you might get another surface that shares the same edge, but maybe that surface will have an easier integral to do. But since they both equal this, they equal each other. Now we're not going to get that complicated, but that's something that higher engineers or higher mathematicians like to use when they're trying to evaluate things like this. So let's save this. This is called Stokes' theorem. And notice what it does. It equates a line integral with a surface integral. All right, so first example that we want to do today. It says evaluate f dot dr, and it should say using Stokes' theorem, where f is the function minus y squared I plus x times j plus z squared times k, where c is the curve of intersection of the plane y plus z equals 2, and the cylinder x squared plus y squared equals 1. It says orient c to be counterclockwise when viewed from above. Okay, now first of all, since they said using Stokes' theorem said the integral along... Now, the other thing to remember is, notice, in this theorem, and I have the theorem right here, this is only good for a simple closed curve, because you've got your surface here, and then you've got your edge looking like this. Notice that curve has to be a simple closed curve. It's got to come all the way around, that you start at one point and end at the same point. You know, we can't have a curve that looks like this, because it's got to be the edge of a surface. All right, so since Stokes' theorem says the integral of f dot dr is equal to the integral over the surface of del cross f dot ds, since they want us to use Stokes' theorem, instead of evaluating this, we're going to evaluate that, because Stokes' theorem tells us that they're equal. So we have some work to do. We've got to figure out what del cross f is, we've got to figure out what the surface looks like, and we've got to figure out what ds is. And then we've got to do a surface integral. All right, so what do we have here? First of all, before I even look at what the surface looks like, let's look at what is del cross f. We need that piece. All right, so our f is this. So the curl, your book likes to write this as the curl of f. I like to write it as del cross f. They're synonymous. That's going to be, we're taking the curl of function f, so we're going to go I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And then I put my x component, my y component, my z component. Okay? And what does that equal? Let's see. This is going to equal the curl of f is going to equal I times, now let's see, eliminate the row and column that I is in, and we have the partial with respect to y of z squared, which is 0, minus the partial with respect to z of x is 0. Minus j times, now eliminate row and column that j is in, so it's going to give me, I went minus, so I'll go partial with respect to x of z squared is 0, minus partial with respect to z of y squared is 0, and then we go plus k times partial with respect to x of x is 1, minus partial with respect to y of minus y squared is minus 2y. So my curl of f is equal to 1 plus 2y times k. Or if I wanted to write it in component form, its components, the x component is 0, the y component is 0, and the z component is 1 plus 2y. Now, in applying Stokes' theorem, I need to know this piece. I also need to know this piece. So now we're going to go to figure out what's ds. Well, let's see. C is the surface of intersection of the plane y plus z equals 2, and the cylinder x squared plus y squared is equal to 1. Okay, well, Well, let's start out here. Does everybody know what x squared plus y squared equals 1 looks like? I think so. We've done this a million times. It's a cylinder. We're going to draw our cylinder in the xy plane, which is the circle. X squared plus y squared equals 1. And you can think of that as, you know, bring this straight up. And it goes forever above and below. Now we want to take the intersection with the plane y plus z equals 2. Well, think, y plus z equals 2. If you're in, let me just draw it apart, and then we'll draw it on here. And if I want to draw y plus z equals 2 by itself, since that just has y and z in it, we all know it's a plane. Since I know I have when y is 2, z is 0, and when z is 0, or when z is 0, y is 2, and when y is 0, z is 2. So it looks like that. And if we sketch it, drag it along the x-plane, it looks like that, right? So think of it dragging that plane along. So if I drag it along here, okay, bringing it, maybe it comes to like here, we can bring that up a little bit. As you can see, when you cut it, slice it, you can see you're getting like an ellipse looking like that. And my curve, they said, they want it to be, when I'm looking down from above, it has to look like it's counterclockwise. So counterclockwise would go this way. So if a little guy is walking along, the unit normal is going to be going up. Okay? So what Stokes' theorem says is, if you want to go f dot dr along this curve, it's going to be the same as del cross f dot ds of the surface. Now, one surface we could take is just this disk that's the interior of the curve. So I'm going to let my s just be that interior, that part of the plane that is being cut off by x squared plus y squared equals 1. Now remember from last time when we did a surface integral, how did we do it? We had to say, how is the surface given? What's the equation for the surface? Well, in this particular case, that surface is the equation y plus z is equal to 2. It's part of the plane. And remember, when we had our surface given by z was given as a function of x and y, then our n ds, which was our ds, all right, was given by minus f partial with respect to x minus partial with respect to y1 dx dy. That's how we represented our ds. So I go, oh, well, my surface here I can given as z equals something in terms of x and y. It's z equals 2 minus y. That's my function of x and y. So my ds is going to be minus fx partial with respect to x minus partial with respect to y1 dx dy, which is going to be, let's see, well, the partial of this with respect to x is 0. The partial of that with respect to y is minus 1, but we're hitting with a minus, which gives me a plus 1, and then a 1 dx dy. Okay? So, going back to Stokes' theorem, we have here, they want us to evaluate this, but Stokes' theorem says that this equals the integral over the surface of del cross f dot ds. So this equals the integral over the surface of, now what was my del cross f? I figured it out a little while ago. It's right here. It was 0, 0, 1 plus 2y. And what was my ds? My ds was 0, 1, 1 dx dy. So I take the dot product of those two. All right, and taking my dot product, this is equal to the integral of 0 times 0 is 1, 0 times 1 is 0, and 1 plus 2y times 1 is 1 plus 2y dx dy. All right, now I'm not finished yet because I got to say, ooh, I'm integrating with respect to x and y. What are my limits of integration? Well, remember, this is the surface that we're doing a surface integral over. But since we're integrating with respect to x and y, we take the shadow of this surface in the xy plane. So we're integrating over that circle. X squared plus y squared equals 1. We're integrating over the circle in the xy plane that has the equation x squared plus y squared equals 1. Well, if I'm integrating over a circle, it cries out, use polars, doesn't it? So we're going to do this integration using polars. I think what I'm going to do here is I'm going to let r equal, one thing though, I do want to check. We said we wanted my unit normal going upward. Just to double check that my unit normal is, notice, if this is going upward, its k component is positive, my k component is positive, so I'm fine. You see, if I wanted it going downward, I'd have to multiply through by a -1 to make it be going downward, and we really need to check it each time. But let's see, I'm going to integrate over that circle, so I'm going to replace x with r cosine theta. I'm going to replace y with r sine theta. I'm going to replace x squared plus y squared with r squared, if I have that. And I'm going to replace dx dy with r dr d theta. And so this is going to become the integral of 1 plus 2r sine theta. dx dy is r dr d theta. What's r ranging from? From 0 to 1. And theta is going from 0 to 2 pi. Okay, and this is a fairly simple integral to do. I'm not going to go do it. It's quite simple, and you would end up with pi. You would end up with pi. Okay, any questions? You guys can finish that, but that's a pretty straightforward integral. But as always, if you don't follow something, come and see me or email me, and I'll write it out for you. Okay, but let's worry about setting them up. Okay, let's do another one. Next one that we want to do is use Stokes' theorem to evaluate the curl of f dot ds. Okay, where f is given by yzi plus xzj plus xyk, and s is the part of the paraboloid z equals 9 minus x squared minus y squared that lies above the plane z equals 5 oriented upward. Well, now first of all, if you ask me, sometimes I get sort of upset with textbooks, because if someone asks me to evaluate the curl of f, dot it with ds, I would try doing it just like that, even though Stokes' theorem says this is equal to the integral if I go along the edge of f dot dr. And we will do it this way, because they're saying use Stokes' theorem to evaluate that, so that means since this equals this, we're going to do this. But let's pretend that we're saying, no, we're just going to go do this way. Well, first of all, notice, if this is f, if I want to get the curl of f, I'm going to go I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, of x component is yz, j component is xz, k component is xy, and that gives me I times, now let's see, partial with respect to y of xy is x, minus partial with respect to z of xz is x, minus j times partial with respect to xy is y, minus partial with respect to yz is y, plus k times partial with respect to x of xz is z, minus partial with respect to y of yz is z. I'm getting 0i plus 0j plus 0k. Why would I want to use Stokes' theorem? You take, if I'm integrating the curl of f dot ds over any surface, and the thing I'm dotting it with is a vector with component 0, 0, 0, I don't care what you dot with 0, 0, 0 with, you're getting zeros. Summing up all those zeros, why would I use Stokes' theorem? You use Stokes' theorem when it makes your life easier. You don't use it when it's harder. You with me? Now, let's tie some things together. Who can tell me? Who can remember anything? Curl curl of f? When the curl of f is 0, when you have a function f, and its curl is 0, what were some of the things that we learned in the previous sections? What does that tell me about the function f? It's conservative, right? And when you're conservative, what does that tell you? That tells you that you can find a scalar function f so that the gradient of f is big F. Remember, these were all equivalent? But now watch here. If the curl of f is 0, then the integral over any simple closed curve is going to be, since this is 0 dot ds, this will be 0. Therefore, this is equal to 0, huh? So remember a few sections ago I said, if the curl of f is 0, then the integral over any simple closed curve was 0, but I said, you know, we haven't really proved it yet. By the way, I'm not proving this because it's an advanced calculus topic, but if the curl of f is 0, then that means the integral over any simple closed curve is 0. For any simple closed curve. And we proved before that if the integral over any simple closed curve was 0, then the integral over any curve was independent of path. Okay, so these 5 things are all equivalent. If you find the curl of f to be 0, you know f is conservative, which means that the function big F has what we call a potential. You can find a scalar function f whose gradient is equal to little f. That means the integral over any simple closed curve is going to be 0. And lastly, the integral of f dot dr will be independent of path. Notice, where does this come from? Well, notice, if you can find this scalar function f whose gradient is equal to f, just go back and notice this. If f is equal to the gradient of little f, remember the gradient of little f is partial of f with respect to xi plus partial of f with respect to yj plus partial of f with respect to zk. And so if you go f dot dr, f is now going to be partial of, let's write it this way, partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, and dr has dx as an x component, dy as a y component, dz as a dz component, and look what you get here for f dot dr. You get partial of f with respect to x dx, plus partial of f with respect to y dy, plus partial of f with respect to z dz, or in other words, if f is just a function of x, y, and z, that's the total differential. So if you're integrating over some curve of f dot dr, you're just integrating df. Well, if you're summing up your delta f's, it's just going to be f at your final minus your f at your initial, which means that I don't care what your path is, you can take multiple paths. This is curve 1, this is curve 2, this is curve 3. As long as they start and stop at the same endpoint, you're going to have the same integral. Okay? So this is important to realize that these 5 things are equivalent. So if you have one of them, you have all the other 4. And they can be very helpful, especially if you're in science and physics or engineering. So for this one, they asked me to use Stokes' theorem. I'm not going to bother, because why should I bother? The curl of f was 0. So I mean, they said to use Stokes' theorem and we could do it, but why bother? If the curl of f is 0 for this guy, our answer is just going to be 0. Okay? Now let's just talk for a second, though, if I really wanted to do it that way. Notice the surface here is the paraboloid. Z equals 9 minus x squared minus y squared. What does the paraboloid look like? Is it a down Z or an up Z? It's a down Z. Looks something like that. The highest it goes is 9, right? Because if you let x and y be 0, you get z to be 9. But we want the part that lies above the plane z equals 5. So maybe z equals 5 is right here, so we're slicing it. So we're just talking about this part of the paraboloid. Okay? Now, we want our unit normal to be oriented upward, like that. So if you have a little guy walking along the edge, and he has a little unit normal on his top of his head, he's going to be having to go this way. Do we all see that? Okay. He's going to have to be going that way. So, if I wanted to, we know from Stokes' theorem that the integral of the curl of f dotted with ds over s was equal to the integral over the curve of f dot dr. I would have to, if I wanted to use this, I would have to get a parametric representation of r. Now, how would I get a parametric representation for that curve? Well, first of all, z is 5. I know z is 5. What is that? It's a circle, isn't it? Well, if z is 5, if I plug a 5 in here, I get 5 equals 9 minus x squared minus y squared, or x squared plus y squared is 4. So if I wanted a parametric representation, any suggestions? Oh, no, I don't want to use polars yet. I want to represent x, y, and z. Well, if you're on the C, notice the shadow of that curve down on the xy plane is just the circle x squared plus y squared equals 4. So why not try taking x equal, what's the radius of that circle? 2. So how about x is 2 cosine t, y is 2 sine t, and z was 5. And that's a parametric representation for that curve as I go around. And t would be going from 0 to 2 pi. Now the only thing I like to check before I go on is, am I going, we said the little guy with the thing on his hat, he has to be going this way. Okay? So let's see. When t was 0, where's the point? Where am I? Well, if t is 0, x is 2 cosine 0 is 1, so x is 2, y is 2 sine 0, which is 0, and z is 5. So when t is 0, I'm at the point 2, 0, 5. I'm right here. Now, how about when t is pi over 2? When t is pi over 2, my point's going to be 2 cosine of pi over 2 is 0, so my x-coordinate is 0. My y-coordinate is 2 times sine of pi over 2, which is 2 times 1, which is 2, and that's 5. Well, 0, 0, in fact, that came right. It was like here, 0, 2, 0, 2, 5 is like right here. So we're going in the right direction, because as we increase time, we're going in the right direction, so it would be correct. Now, what they want us to do is they want us to do the integral along the curve of f dot dr. And let's just review how we would set this up. First of all, our r is, the x-coordinate was 2 cosine t, the y was 2 sine t, and the z was 5. But we're not dotting with r, we're dotting with dr. So what's dr? Well, you just differentiate each of these term by term. So the derivative of 2 cosine t is minus 2 sine t. The derivative of 2 cosine t is, of 2 sine t is 2 cosine t. And the derivative of 5 is 0. Plus you'll have that little dt there, because it's dx dt, dt, dy dt, dt, dz dt, dt. All right, and what was f? Coming back here, here's what f was. That's what f was. So if we want to know f dot dr, we're dotting this vector with this vector. So we're going yz times minus 2 sine t plus xz times 2 cosine t plus 0 times xy. So forget that. It's just 0. And I forgot my little dt at the end. I'll just put in there. Are you all with me? Now they want me to do the integral of f dot dr. So I want to do the integral of minus 2 yz sine t plus 2 xz cosine t dt over that curve. A little bit of problem here, people. I got a y, I got a z, I got a t. How can I make this just in terms of t's? Aha! Remember, this is your x, this is your y, this is your z along the curve. So where I see y, I'm going to put in 2 sine t, excuse me. Where I see z, I'm going to put 5. All right? Plus, where, this is bracket, bracket. Where I see x, I'll put in 2 cosine t. Where I see z, I'll put 5. And then I have cosine t dt. And what's t ranging from? 0 to 2 pi. Okay, so let's see. This gives me, I think a new sheet of paper would be helpful. The integral from 0 to 2 pi of 2 times 2 is 4 times 5. I have minus 20 sine squared t plus 20 cosine squared t dt, which I could factor out the 20 if you don't mind. Okay, and then I have, would you mind if I wrote this as cosine squared t minus sine squared t dt? Okay, now we got to figure out how to do that integration. All right? You could, if you wanted to, replace cosine squared with, in fact, let's do it that way. We'll replace cosine squared with 1 plus cosine 2t over 2. We'll replace sine squared with 1 minus sine 2t, excuse me, cosine 2t over 2. And if I simplify that, what do I end up with? Well, you're going to have 1/2 minus 1/2. Cosine 2t over 2 minus a minus is plus cosine 2t over 2. So that gives me 2 cosine 2t over 2, which is just cosine 2t. And some of you might be saying, Mrs. Strocko, why did you do it that way? Because I know the identity that cosine squared t minus sine squared t is cosine 2t. And if you knew that, you would be saving all the time. But since we always said whenever we had cosine squared or sine squared, we use that identity, I went that way. I can do this integration fairly quickly. It's sine 2t over 2. Just double checking, the derivative of this should be given what's inside. I get cosine 2t times 2, the 2's cancel. So I have 10 sine 2t from 0 to 2 pi, which gives me 10 sine of 4 pi minus 10 sine of 0. But sine of 4 pi and sine of 0 are both zeros, so I got the 0 that I got before. Now, on a test, if they just asked me to integrate that f dot, if the original problem said to evaluate, oops, that's not that one. The original problem, if they didn't say use Stokes' theorem and they just said evaluate this, shoot, I'd figure out what the curl of f is. If it's 0, I'm done. But since they said use Stokes' theorem to evaluate, they wanted me to change it to an f dot dr, represent my curve parametrically, and go that way. Okay? But as you can see, quite miraculously, we got the same answer. Let's look at this one. Use Stokes' theorem. Now this one, you look at the curl of that f, that's pretty bloody. The curl of f for this guy is pretty awful. I think I will use Stokes' theorem because it's going to make my life a little bit easier. So this one cries out, use Stokes' theorem. So Stokes' theorem says that the integral over my surface of the curl of f dotted with ds is equal to the integral over the closed curve, which is the edge of the surface, of f dot dr. And the reason I'm not going to go ahead and evaluate curl of f is that's going to be pretty awful, figuring out the curl of that guy. It's going to be, you got an e to the xy. That's not going to be too nice. So now, what is my surface here? My surface is the hemisphere. X equals square root of 1 minus y squared minus z squared, oriented in the direction of the positive x-axis. Now notice, if you take the equation x equals square root of 1 minus y squared minus z squared, if you square both sides and add your y squared and your z squared, this is part of the sphere that has center, origin, and radius, the origin, right? So if I wanted to draw that hemisphere, I'm not very good at drawing it. You're going to have a radius of 1. But we're not getting the whole thing. We're just getting the part, you with me? Sort of the part that's in front of the YZ plane, because it's x equals square root. So if I had like the y-axis here and the z-axis here, I'm getting that part here, and then you think of your ball setting, you know, it's coming like this, you with me? It's just it's the part of the sphere that's with the positive x-axis. Part of sphere with positive x-axis. You with me? Now, they want it oriented in the direction of the positive x-axis. Positive x-axis is pointing out this way. You with me? So if I have my little guy, and he's walking along here, and he's got his little normal on his head, because it's got to be pointing in the positive x-axis direction, how's he going to have to walk? This way. Because if he walks this way, his left arm's sticking in, you with me? This is my little guy's walking in, this is his left arm sticking in, and he would have to be going with this orientation. All right, so they want us to figure out the integral along this curve of f dot dr, and what's my curve? The edge of the hemisphere. This is my curve, so I have to get a parametric representation for that, for the edge. All right, now that curve has x equal to 0, right? So when x is 0, we have y squared plus z squared equals 1. It's a circle of radius 1. So my parametric representation is x is going to be 0. How do you want to represent y and z? Y equals cosine t. That sounds good. And z equals sine t. Now I want to check the way I'm going. I want to make sure I'm getting that counterclockwise. So let's look. If I let t be 0, where am I? X is 0, y is cosine of 0, which is 1, and z is sine of 0, which is 0. So I'm going to be at the point 1, 0 right here. Now if I increase t just a little bit to pi over 2, x is 0, y is cosine of pi over 2, which is 0, and z is sine of pi over 2, which is 1. So at t equals 0, I'm here, and t equals pi over 2, I'm here. So am I okay? Yeah, with increasing time, I'm going in this direction. With me? Because you have to have your orientation. Otherwise, you might get an answer of pi, and the answer in the back of the book is minus pi, because you had your orientation going the wrong way. So now we got to figure out f dot dr, but notice r is the vector 0, cosine t, sine t. So dr is, notice it's dx dt dt, dy dt dt, dz dt dt. So if I take the derivative of that, I get 0. Derivative of that is minus sine t. Derivative of that is cosine t dt. And f, remember, was x component is e to the xy cosine z, x squared z, and xy. So f dot dr is going to be e to the xy cosine z times 0, which is 0, plus x squared z times minus sine t, plus xy times cosine t. Now before I do my integral of f dot dr, I want this whole thing to be in terms of t's. So where I see, remember, this is my x, this is my y, and this is my z as I move along that curve. So where I see x, I plug in 0. Well, geez, that's great, because 0 times anything is 0. And where I see x, I put in 0. 0 goes there again. So we're integrating 0 plus 0 plus 0 dt as t goes from 0 to 2 pi, but the integral of 0 is 0. And that one was pretty easy to do. Are we all with me? Okay. So this one was one in which doing that would be prohibitively difficult. Doing this was very easy. And that's why you have Stokes' theorem, because if the one integration is difficult, you'll do it the other way. Okay. Let's look at this one. Use Stokes' theorem to evaluate f dot dr. In each case, and we're going to do a few of these, in each case, C is oriented counterclockwise as viewed from above. And C is the boundary of part of the plane 2x plus y plus 2z equals 2 in the first octant. Okay, so first of all, they said use Stokes' theorem, so we're not going to be doing f dot dr. We're going to be doing the integral along the curve of f dot dr is equal to the integral over the surface of the curl of f dotted with ds. So we're going to evaluate this one. But first of all, I got to figure out, what does the surface even look like? So what does the surface look like? C is the boundary of part of the plane that's given by the equation 2x plus y plus 2z equals 2 in the first octant. Okay, well, first of all, let's just get our points on the axes, all right? So let's see. If I let y and z be 0, I have 2x is 2, and so I end up with x is 1. So I have the point 1, 0, 0. If I let x and z be 0, I get y is 2, so I get the point 0, 0, 2. And if I let x and y be 0, I can see z is 1. 0, 0, 1. Okay. Now they said we want to have orientation so that it's oriented counterclockwise. So we want to be going this way. Counterclockwise is we view from above. So the little normal is going to be coming out this way. You with me? It's going to be coming upward because the little guy would have to have it on top of his head coming this way in order for him to be walking with it to his left. So where is my surface? It's just this little triangle right here. We want to integrate over that surface. Okay? To evaluate this. So first of all, I think what I want to do is I want to get what my, I want to figure out what del cross f is. Okay, what del cross f is. Let's see, which one are we on? Okay. All right, so we want to figure out what del cross f is, and then we got to figure out what ds is. All right, so first of all, let's get del cross f. So del cross f is equal to I, J, K. And let's see, here's my f. So I'm going to go partial with respect to x, partial with respect to y, partial with respect to z, e to the minus x, e to the x, e to the z. Okay, and that's going to give me, let's see, I times, low in column that i's in, I get partial with respect to y of e to the z, that's good, that's 0, minus partial with respect to z of e to the x is 0, minus j, eliminate row and column j is in, I get partial with respect to x of e to the z is 0, minus partial with respect to z of e to the minus x is 0, plus k, let's see, partial with respect to x of e to the x is e to the x, partial with respect to y of e to the minus x is 0. So this is equal to the vector 0, 0, e to the x is my k part. Okay, so I've got my del cross f. I've got my curl. What do I have to do yet? I got to figure out my ds. Okay, so we got to get our ds. Well, remember, if you can have your surface in the form of z equals f of x, y, your ds was quite simply minus the partial with respect to x minus the partial with respect to y, 1, times dx dy. We did that last time. So here, we can solve for z. Let's see. 2z equals 2 minus 2x minus y, or z equals, if I divide by 2, 1 minus x minus a half y. Okay, are you all with me? Because the surface was given by 2x plus y plus 2z equals 2. So I got 2z equals 2 minus 2x minus y, divide through by 2, z equals 1 minus x minus a half y. So ds here would be, now let's see, the partial with respect to x, because this is z equals f of x, y. Partial with respect to x is minus 1, so we take the opposite of it, which gives us 1. Partial with respect to y is minus a half, but we take the opposite of it, which gives us a half. And then we got 1 dx dy. Okay, so now we're ready to do del cross f dot ds. So here's my del cross f. So del cross f dot ds is going to be, let's see, 0 times 1 is 0. 0 times a half is 0. And e to the x times 1 is e to the x dx dy. Okay, so we are ready to do our integration of the integral of e to the x dx dy. Now, we've got to figure out what our limits of integration are. We're integrating with respect to x and y, so what do? We take the shadow of our surface onto the xy plane. So I look at that and I say, oh, my shadow's down here. Okay, so this is the point 1, 0, 0, and this is the point 0, 2, 0, and so we're integrating over this region. Okay, well, I think, let's see, this equation right here, y equals, if I want to write it as mx plus b, my slope is, if I go from this point to this point, my change in y is minus 2, my change in x is 1, so that's minus 2x, and my y-intercept is 2. All right, so I think I'm going to integrate e to the x dy dx at y is going from 0 to 2 minus 2x. And if I sum all those up, my x is going from 0 to 1. And this is not a hard integral to do, so I'm not going to, there's a little part there where you got to do the integral of x dx. There's a little piece where you're going to get the integral of x e to the x dx. Just use parts. Or if you're tired, look in the back of your book. They have your integral tables. Okay, or if you want to turn on Maple or the TI-89 and do it, that's fine. But this integral, if you go ahead and do it, it's not all that hard to do. You're going to end up with 2e minus 4 for your answer. Okay, I want to do 2 more examples, and watching me integrate, I think you've watched me integrate enough this semester. Let's do 2 more. Use Stokes' theorem to evaluate the integral f dot dr. In this case, c is oriented counterclockwise as used from above. This is your f, this is your c. All right, so first of all, you say, okay, they want me to use Stokes' theorem. No problem, Ms. Strocko. The integral along the curve of f dot dr, according to Stokes, is also equal to the surface integral of del cross f dot ds. So I have 2 things. I have to figure out del cross f, and I got to figure out ds. We'll do del cross f first. Here's my f. So my curl is I, j, k, and we're going to put in partial with respect to x, partial with respect to y, partial with respect to z, and we have components x, y, and x squared plus y squared. Okay, and if we do that, we get I times partial with respect to y is going to be 2y, minus partial of y with respect to z is 0, minus j times partial with respect to x of x squared plus y squared is 2x, and partial with respect to z of x is 0, plus k times partial with respect to x of y is 0, partial with respect to y of x is 0. So it looks like I have my curl is the vector 2y minus 2x and 0. Okay, is what I have for my curl. All right, so that's my del cross f. Now we have to get our ds yet, so I didn't even look to see. What is c? c is the boundary of the part of the paraboloid z equals 1 minus x squared minus y squared in the first octant. Okay, so we normally have a paraboloid that comes down like this, and you got your little circle here, but they're only taking the part of the paraboloid that's in the first octant. So we're just taking this little piece here, and we're taking the part that goes to here and the part that goes to here, and this is our surface. Okay? And if we continue, what we're going to have to do is we're going to figure out what our ds is, and then the area that we're integrating over is going to be the shadow of this paraboloid down here in the xy plane. But let's look. First we have to get our ds. We have to get our ds. Remember, if the function is given in the form of z equals f of xy, your ds is quite simply minus fx minus fy1 dx dy. And you have your f of xy because your z is given in the equation of z equals 1 minus x squared minus y squared. So my ds is going to be, what's minus the partial of that with respect to x? Well, the derivative of minus x squared is minus 2x. Take the opposite of it, I get 2x. Take the partial of that with respect to y, I get minus 2y, but take the opposite, I get 2y. And then 1 dx dy. So when we want to put together the curl of f, dot it with ds, we're taking the dot product of this vector with dx dy at the end. When you go this times this, you get 4xy. That times that minus 4xy. That times that plus 0 dx dy, and heavens, this is nice. So when they want to do the surface integral of that, they're doing the surface integral of 0 dx dy, and what do we get? 0. So a lot of these, they turn out to be 0, so you know, go, oh, this isn't bad. But if it did not turn out to be 0, you would then have to figure out, how do I integrate over this region right here, because it's the shadow of your surface onto the xy plane. Now lastly, the last one that we want to do is we want to verify Stokes' theorem is true for the given vector field and surface, f equals blah, 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 and S is the part of the plane 2x plus y plus z equals 2 that lies in the first octant oriented upward. So in other words, we've got to set up, since Stokes' theorem says the integral over the curve of f dot dr equals the integral over the surface of del cross f dot ds, we have to do this one and evaluate it, this one and evaluate it, and if we don't get the same answer, I guess we got to go back and fix it up to find out what we did wrong. Now, let's do this one first, the harder of the two. Okay, first of all, what does my curve look like? Well, first of all, what's my surface? My surface is, they're taking the plane 2x plus y plus z equals 2, and we're looking at the part of the plane that's in the first octant. Well, let's draw that part of the plane that's in the first octant. If I let y and z be 0, I can see x is 1. So we're at the point 1, 0, 0. If I let x and z be 0, I see y is 2. 0, 2, 0. And if I let x and y be 0, I see z is 2. 0, 0, 2. Since we are doing this problem with the surface oriented upward, my unit normal's coming out like this. Think of the little guy walking with this on his head. He'd be going this way with his left arm sticking in, and so we have to go this way. Now, to do the integral over the curve of f dot dr, we've got to integrate along the border. Unfortunately, people, I don't have one nice little pat equation for this border, do I? Because it's 3 line segments. So to do the integral along the curve of f dot dr, if I call this maybe curve 1, this curve 2, this curve 3, I'm going to have to integrate over C1 plus integrate over C2 plus integrate over C3 and add all 3 of those up. That's why in this particular one, if someone asked me to evaluate f dot dr and they didn't tell me I had to do it both ways, I would go do the other way because that'll be 1 integral. This is going to be 3. Okay, but it's not too painful, so let's do it. Okay, let's get C1 first. I'm going to say C1 is going from 1, 0, 0 to 0, 2, 0. It's this line segment from here to here. So what's good is we have to remember, how do you represent a line segment parametrically? Well, remember what you do. Let's just review. Your x is going to be your initial point, which is 1, plus, then subtract this one minus that one. In fact, let me just put the formula down for you that if you have forgotten. If you're going from x naught, y naught, z naught to, let's say, x1, y1, z1, and you wanted to do it parametrically, your x is going to be your first point plus t, and then subtract your final minus your initial. Your y is going to be your first point, y naught, plus t times final minus initial. And your z is z naught plus t times final minus initial. And that would be your parametric representation. Okay, so using that, if we're going from 1, 0, 0 to 0, 2, 0, my initial point's 1, and then I'm going to go 0 minus 1 is a negative 1 times t. So I have x equals 1 minus t. Y equals your first point, which is 0, plus 2 minus 0, which is 2 times t. So y is 2t. And z, you could say it's 0, it starts 0, ends 0, so it's going to be 0, but it'd be 0 plus 0 minus 0 is 0t. So c is 0. Now notice your t's going from 0 to 1. Notice if you let t be 0, you get 1, 0, 0. If you let t be 1, you get 1 minus 1 is 0, 2 times 1 is 2, and 0. So you get, when t is 0, you get your initial point, t equals 1, you get your final point. So my r is the vector 1 minus t, comma 2t, comma 0, your x, y, z. So your dr is going to be, derivative of that is negative 1, derivative of that is 2, derivative of that is 0, times dt. So if we want to do f dot dr, here's your f. What is f dot dr here? Let's see. F dot dr is going to be x times a negative 1 is minus x, plus y times 2 is 2y, plus x, y, z times 0 is 0, times dt. So we're going to be integrating from 0 to 1 of minus x plus 2y times dt. But people, I have a problem here. This is in x's and y's, and I got a dt here. So what am I going to do? Remember, this is x, this is y, this is z. So you're going to plug in here. Where you see x, you're going to plug in 1 minus t. Where you see y, you're going to plug in 2t. Okay, and this looks like it's what? Let's see. We're integrating f dot dr. This is just for C1 so far. Is the integral from 0 to 1 of, let's see, minus 1 minus a minus is a plus t plus 4t dt, which gives me the integral from 0 to 1 of 5t minus 1 dt. I think you guys can handle that. I did it earlier, and you get 3/2 for your answer. Okay, then we're going to have to do it for C2 and for C3. Okay, but coming back here, we just figured out the integral over C1 is 3/2, so I'll put that down there so I have it. Okay, so now we got to do C2, unfortunately. So what is C2? C2, here's my picture. C2 is going from 0 to 0 to 0, 0, 2. Okay, so my x is my initial point 0 plus the difference 0 minus 0 is 0t. So x is just 0. My y is going to be 2 plus 0 minus 2 is negative 2t. So y is 2 minus 2t. And z is 0 plus 2 minus 0 is 2 times t. Z is 2t. Check yourself. If you plug in t equals 0, you should get the first point. I get 0, 2, 0. That's good. If I plug t equals 1, I should get the last point. T equals 1 gives me 0, 2 minus 2 is 0, 2 times 1 is 2. It works. So my r is going to be 0, 2 minus 2t, 2t. So dr is your derivatives, 0, minus 2, 2, and of course you'll have your dt at the end. So coming back here, f dot dr is going to be 0 times anything is 0. Minus 2 times y is minus 2y, plus 2xyz. And then we do have the dt at the end. All right, except we have to plug in. Remember, this is your x, this is your y, and this is your z. So y is 2 minus 2t. So I have a negative 2 times 2 minus 2t. So I'm putting that in for y. But since x is 0, thankfully that whole thing is 0. So we're just integrating minus 2 times 2 minus 2t dt as t goes from 0 to 1. And I did do that earlier, so I don't think you need to sit there and watch me integrate. I got a negative 2. Okay? And so this piece right here is minus 2. Now we have to do the third one. So the third curve which can be quite tedious. That's why I can't give you too many of these on your test. C3, you're going from 0, 0, 2 to 1, 0, 1. So what are my parametric representations? X is going to be 0 plus 1 minus 0 times t. Y equals 0 plus 0 minus 0 times t. And z is going to be 2 plus 0 minus 2 is a negative 2 times t. So my r here is the vector, the x component's 2, the y component 0, and the z component is 2 minus 2t. So dr, derivative of that is 1, differentiating with respect to t, that's 0, minus 2 dt. And if we take f dot dr, we're dotting this vector with this vector. We get 1 times x is x, 0 times anything is 0, minus 2xyz dt. Except on this surface, this is x, this is y, this is z. So we get the integral of f dot dr is equal to, for x I replace it with t, but notice it put a t here, but y is 0, so that part drops out. So we just have 1 dt dt as t goes from 0 to 1, and I already did that one. I got a half. So that final integral turned out to be a half. And so if we add these up, 3 halves and a half is 2, minus 2, all that to get a 0. All of that to get a 0. But they asked us to do it both ways. So we just did it this way, and we saw it was ugly because my surface, my curve had 3 pieces. So now we have to do this one, and hopefully it'll be a lot quicker this way. We're now going to go back and get the surface. We want to figure out what is, because on this side we got a 0. Now we're going to do it this way. So we want to figure out what's the surface integral of the curl of f dotted with ds. So we have to find the curl. Why don't I'm not going to do it. The curl of f, you guys have gotten pretty good to it. Here's your function f, and if you do the curl, I did it a few minutes ago, I got the vector xz minus yz 0. That's not one that I think we need to work on. Okay, you're pretty good at that. But I think the ds is something that we forget how to do. Remember, to get your ds, if your surface can be given as z equals a function in terms of x and y, and mine is, because my surface is given by this equation. I can solve for z. I get z equals 2 minus 2x minus y. We know that ds from last time is given by minus fx minus fy 1 dx dy. So I can get that quite simply. ds is going to be, let's see, minus the partial of that with respect to x is a negative 2. Take the opposite of it is 2. The partial of that with respect to y is a negative 1. The opposite of it is 1. We got a 1 there. dx dy. So del cross f dot ds is going to be the vector xz minus yz 0 dotted with 2, 1, 1 dx dy. Okay? Which is going to give me, let's see, 2xz minus yz dx dy. Okay? So now we have what del cross f ds is, but we're integrating over, let me bring my picture back if I can find it. Oh good, here it is. We're integrating over this surface. Right, that surface right there. So we have del cross f dot ds is, we're integrating over the surface of 2xz minus yz dx dy. Now notice, since we're integrating with respect to x and y, we shouldn't be having z's in here. Well, that's very easy. To get rid of that, we have right here, z on the surface is 2 minus 2x minus y. So where I have z, I can replace it with 2 minus 2x minus y. 2 minus 2x minus y. It can be dx dy or dy dz. To get my limits of integration, you take the shadow of this surface, since we're integrating with respect to x and y, onto the xy plane. Well, I think I can do that quite simply. Let's see. On the xy plane, I have the point 1, 0, 0, and the point over here is 0, 2, 0. And my shadow in the xy is right here. This equation right here is y equals, the slope is down 2 over 1, so it's minus 2x plus 2. I think I'm going to do my integration with respect to y and then with respect to x, because what's y ranging from? From 0 to 2 minus 2x, and if you sum all those up from 0 to 1. And this, people, I mean, it's a polynomial, and it's a pain to do. We're not doing it. You would get 0. Okay? Now, let me just take 5 minutes to talk about something that I think is important. No more tedious problems to do, but why does anybody care about this? Why do we care about the curl? When I first introduced the curl, I tried to give you the sense that the curl sort of measured how you're rotating around like a fluid field is going around it. Now, Stokes' theorem says the integral over the curve of f dot dr is equal to the integral over the surface of the curl of f dotted with ds. Okay, now what I'm going to do is let's assume that this vector field that we're looking at is going to be a velocity vector field. So if I have some fluid, like at this point, what's f at that point? It's how the fluid is flowing at that point. You with me? So it's the f is standing for the velocity of the fluid at some point in three-dimensional space. So maybe you have your fluid, like if your fluid was going circular, like at this point you would see like little vectors going around like this maybe. And that's showing that at this point right here the fluid's going that way, at this point the fluid's going that way, at this point the fluid's going that way. So it's showing fluid. Now notice, let's look at this side right here. If you had a point right here and you had some curve around the point and you're doing the integral of v dot dr, okay, remember what when you take the dot product of something, you're taking the magnitude of this times the magnitude of this times the cosine, that's your dr, times the cosine of the angle between them. Well, if r is pointing in this direction, and maybe v, so that's your little dr right here like that, and your v's right here, when you take the magnitude of v times the cosine of the angle, you're getting the component of v that's going in the direction of the circle. When you take the magnitude of v times the cosine of the angle times the magnitude of dr, this piece right here is giving the component of v in the direction of the circle. So you're saying how much of the fluid, how much of that velocity vector is actually going in that circle, and then you're multiplying it times your delta r, and you're actually computing how much, what's your tendency to go around in that circle. So this side of the equation is measuring your tendency to flow around the center of that circle. Now on this side, you could rewrite this del cross F as dot n ds, where n is some unit normal. This is a vector and this is a vector. Now, let's take a very small point and let's take a very small little circle around that point. Well, if that's a very small point, the curl evaluated at any point is approximately equal to the same as the curl at the center, because I'm taking it really, really small. So we could write this side right here, as the magnitude of del cross F times the magnitude of n times the cosine of the angle between them times ds. All right, now look here. What if I choose my unit normal on my surface to be in the direction of del cross F? Then the angle between them is 0, and the cosine of 0 is 1. All right, so I'm going to choose my unit normal. I'm going to choose my surface so that my unit normal is going in the same direction as the curl. All right, so I'm pointing my unit normal in the direction of the curl. All right, in which case you're getting cosine of 0, which is 1. So this thing's equal to the magnitude of del cross F times ds. Well, since I'm saying this is a real tiny little circle right here, a real tiny little disk, I'm going to approximate that del cross F for the whole little area as what it is at the center of the circle. I'm going to pretend it's almost like a constant. So you have surface area of ds, well, that's just a little circle, so it's whatever the area of the circle is. Let's say the radius of the circle is like maybe pi a squared. So I showed on this side, this was tendency to rotate, right? And as you can see then, what your curl turns out to be, the magnitude of your curl is equal to your tendency to rotate divided by some area. And notice, if you chose little n not to be in the direction of del cross F, you'd have the cosine of some angle which would be less than 1, right? Because the maximum that cosine theta can be is 1. So when you pick your surface, when you pick to make your little unit normal to be in the same direction as the curl, this is maximized and you get maximum rotation. So the way I think about it is this. You've got this three-dimensional fluid flow. You have like this little bar, this little unit normal, all right? This little unit normal that has this little disc around it. Now, you can pick that, and you're going to look to see how that's flowing around. Well, if you want to get the maximum fluid flow on that disc, what you have to do is you've got to point your unit normal so it's in the direction of the curl. So the curl is giving you what direction this little handle needs to be, so that if you put it in the fluid, you'll see the thing rotating around the most. So it's pointing you, that's really pointing you perpendicular to the disc that you would get to get maximum fluid flow. If you take fluid mechanics or something like that, you're going to do a whole lot of this type of stuff. But we really can't equate that without Stokes' theorem. Stokes' theorem is what's enabling us to show how the curl really is giving us tendency to rotate. Now what you people need to do for next time is read over pages 1157 to 1160. Don't get wacky in terms of evaluating the integrals. If you haven't access to a TI-89 or a 92 or to Maple, or to tell you the truth, if you have access to the student edition, set up your integrals, set up your parametric representations for your curves and for your surfaces, and then just check to see if your integrals are equal to each other. I know at the end of the semester you have a finite amount of time for studying, so the most important thing is setting up these integrations. And then, do a couple of them all the way to the very end. The ones I like are 1 through 9, the odds, and 13. And then fortunately or unfortunately, I'll see you next time for our very, very last Calculus 3 lecture. Okay, see you next time. Bye-bye.